Hello, everyone. I'm here today to talk about xCluster Replication. xCluster Replication is an asynchronous replication we use at Yugabyte to replicate data between different data centers. It's got a lot of power and a lot of flexibility, and we're going to look at how it works, why you might use it, what's coming down the pipeline for it, and some use cases where it makes a big difference. So before we get started, I'd like to introduce myself. So I'm Tim Fawkes. I'm the Director of Data Engineering for the West Coast of the United States. I'm joined today by Sandeep Lingam, who is the Director of Engineering at Yugabyte. And it's our pleasure to talk to you today, and I hope everyone's having a great DSS so far. So before we start talking about asynchronous replication, I'd like to talk about the normal sort of replication we do inside Yugabyte, and that's synchronous replication. Synchronous replication is great. It allows you to have different architectures which guarantee consistency with very, very high availability. So if we look at a couple of our most common architectures, the first is I have a single region, and that can be a cloud provider region. It could be a data center, anything like that. And inside that, I break that down into multiple zones. Again, zones being a cloud terminology. Inside a data center, you're probably thinking about racks if you're running on bare metal. This sort of topology works really well. If I look at, I'm just going to use the terminology, single region, multi-zone. In this case, when I do a write, the write gets replicated across. We have, say, 3 copies of the data and 3 failure zones. So each one of these failure zones or availability zones has its own copy of the data. When I write the data, it goes to one of the copies of the data, and that will replicate it across to the other 2. And when they come back and say, yes, we've got it, so we've got 2 out of 3 forming a quorum, then we can acknowledge that right to the client. This is synchronous replication, pseudo-synchronous replication, because the writes actually go in parallel to the different availability zones, but from the client's perspective, it looks like it's synchronous. That means that we know when we respond to the client that we have that data across multiple different data centers or different availability zones. If those availability zones are close together, then it's very, very fast to do. It's strongly consistent. We're always strongly consistent. And it gives you really high availability zone. If I lose a single availability zone, the remaining 2 availability zones can still form quorum, which means that they can still serve your reads and writes. And that means that the loss of an availability zone doesn't affect you in any way, shape, or form. Another pattern we see a lot of is single cloud, but multiple region. So I have, in this case, something like US East, US West, and US South. When I write, I want to go and write again to a quorum of those nodes. I need to guarantee consistency. That works well. However, these regions are typically far apart, and the speed of light actually comes into play. As we're replicating the data between those regions, there is a cost. The cost is in terms of time and latency. So if I'm replicating between, say, US East, US West, and US South, there's probably going to be around about a 70 millisecond delay for every piece of data I write, simply because the speed of light is in the way. Now, the advantage of this topology is I can lose an entire region and still keep running with guaranteed consistency and 100% availability. We've actually had some customers in production who are unfortunate enough to be able to have lost a region and in an unplanned event, and they just kept running. And so very, very high availability, but you do have that latency penalty. Now, on the read side, there's ways around this. Yugabyte has some different architecture that has things like follower reads and read replicas, where you can say, I don't really care if I don't get the latest copy of the data, but I want to read very, very quickly. And this is great for product catalogs, shopping carts, things like that. However, because we are a CP database, we guarantee consistency. We always have to have that speed of light issue when we go across large distances. So that's where asynchronous replication comes in. Let's say I've got some data which is important. I want to be able to do very fast reads and very fast writes. I have a data center on the east coast of the US and a data center on the west coast. I want them to be consistent, but I'm okay with a little bit of inconsistencies for the short term, so long as they eventually catch up, and eventually is normally very quick. This is where xCluster replication comes in. It's asynchronous. And so each one of those clusters is typically in a single region with multiple zones. So they get the availability that we just spoke about inside a single region, but then they replicate the data asynchronously to the other region. That means the speed of light doesn't come into play from the application side because I've just written to my local region and we're transmitting the data asynchronously to the other end. That gives us the ability to read it very quickly on the other end without having to suffer the wait for the speed of light to replicate that across the country. The nice thing about this is because the two regions actually end up with the same data, they can serve as DR copies as well. So if I was to lose one of these entire regions, I still have another full complete set of the data in the other region. So let's look at some use cases where we might use xCluster. There's a couple of supported topologies, and before we get into the use case, I want to go through these very quickly. The first is an active-passive scenario. So effectively, I have a source cluster and a sync cluster. My source cluster is taking both reads and writes, but my sync cluster is only taking reads. I'm replicating the data one directional, so from my source cluster to my sync cluster. And this is very, very common in DR scenarios where I've got an active cluster that's serving all the traffic, but I want to make sure that if something happens to that cluster or the region it's in, that I have another cluster which has all the data that I can have it take over the traffic if that primary cluster fails. You do get very low latency on the reads at both source and sync cluster. And what we typically find is most people like this scenario. They will actually tend to be replicating the data both directions. So where it says unidirectional async replication, in reality, what you really want is bidirectional, but you're only writing to one cluster at a time. And the advantage of having it bidirectional is if my main cluster falls over and I fall and all my traffic now starts going to my DR cluster, that DR cluster should replicate the data back to the source cluster when it comes up. So you don't have any inconsistencies in data, even if the loss of a cluster occurs. This scenario is also really useful for live migrations. If I'm moving from bare metal into the cloud or from one cloud provider to another cloud provider, it's really useful to be able to move the data asynchronously and see the data and to have the two data centers kept in sync as I perform the application migration. The other common pattern we see is two different regions again, but this time we've got active-active communications. Now, in this case, I'm writing to both clusters at the same time. There is no concept of a main cluster versus a DR cluster. They are both active. Now, what we find, and this seems to be particularly prevalent in financial service institutions, that they have a 2 DC setup. Many financial services companies have exactly 2 DCs. With the replication we spoke about earlier, we can't do that with 2 DCs because we need to have quorum. So that synchronous replication has to have an odd number of copies of the data. Having 2 DCs can work well if you're doing this sort of active-active setup on that replication, that asynchronous replication. Now, obviously, if I have this scenario, if I'm updating the same record on both clusters at the same time, which is possible, then I can have a conflict on that same record. We have a conflict detection and resolution, and that resolution always falls down to last writer wins semantics. So whichever was last written will win that tie. There are some caveats with this scenario. You want to avoid certain things like a unique index. If I've got a unique index and I write a record to cluster 1 and I write a record to cluster 2, neither of which violates that unique index by themselves, but when they get merged together, they form something which violates that unique index. That's bad. So you really want to avoid those sort of unique indexes, unique constraints, and also counter columns or serial columns in primary keys, because they're not going to generate sequence numbers that are globally unique. They're going to try and replicate some of that data between them because each cluster is truly independent. So one use case that I've seen, and this is a fairly common pattern, is major financial services company. They have 2 data centers. They're on different sides of the country for the DR capabilities, because if they lose one, they want to make sure that event that took one out doesn't take the other one out. So they're on opposite coasts. Now, for this particular financial services company, they have very low latency requirements, and that's on both reads and writes. They have data tied to a particular geography. So when they look at a customer data, if the customer is on the West Coast, they will always go to the West Coast to read that person's data. Even if that person travels to the East Coast temporarily, the data will still be read from the West Coast. So it's still the latest copy of the data, but they've made sure that when they write the data, they don't get any of those conflicts I just spoke about. Each person has a known home, if you will, a region that is their main locality, and that solves the problem of those conflicts. The advantage of this is obviously that if one of these fails, they have a full copy of the data for DR purposes. They will obviously get a bit of latency there if there's something going across country, but most of the time this works really well. And I've seen this sort of scenario in several of the major financial services institutions who use Yugabyte. All right, so let's look a bit at xCluster. How does it work today? So before I get into that, the first thing I want to do is introduce a bit of terminology. And the terminology is a tablet. Everyone is familiar with SQL databases and the fact that they create tables. Those tables are broken up by Yugabyte into tablets, and a tablet is a subsection of the data inside that table. This is all automatic. It's transparent to the user. As far as anyone using the database sees, it's just a table, and they don't know where the data lives, and they don't need to. We break that data up into tablets. A tablet is a subsection of the data inside that table. So it's a set of rows, and it's really difficult to predict which rows will go into which tablets. It's all transparent to the user. Now, typically, this diagram shows that effectively I've broken up into 6 tablets. I haven't shown the fact that we want 3 copies of the data, and so each one of those tablets will actually be replicated 3 times. This is just trying to simplify things. So now we know what a tablet is. Let's look at how xCluster works today. We have our 2 discrete regions, 2 discrete clusters in 2 discrete regions. We're transferring data back and forth between them. It doesn't matter whether it's active-active or active-passive. One of the nice things about this xCluster replication is the topologies of the source cluster and the destination cluster can be different. So if I've got an active-passive scenario for DR, for example, my active cluster might be on faster hardware because it's going to take most of the traffic. I might be able to use cheaper hardware on my passive or my DR cluster because the probability of me failing over to that is lower. And even if I fail over to that, I'm okay with it because it's a disaster scenario taking a bit longer. So I can actually save some money on the hardware, and the topologies don't need to look identical between them. In today's world, each tablet is replicated asynchronously between the source and the destination clusters, but they're done independently, and that's key. And we'll cover some reasons why that's key in a moment. We make sure that the writes are batched together. So if I write a single record into one cluster, I'm writing at a reasonable clip, I'm not just going to send one record across to the corresponding tablet on the other side. I'm going to send a bunch of those records together. It makes it much more efficient. When we do this sort of replication, and it doesn't really matter whether we're using SQL or the Cassandra CQL style interface here, the destination is pulling the records from the WAL file on the source cluster and then inserting them directly into our underlying storage layer. We have effectively a key value database called docdb underneath that, which stores the data. Because we're inserting that data directly into that underlying storage tier, things that happen at higher layers, like triggers in SQL, don't get fired. So if you have triggers, this probably isn't a good use case for you, because the trigger will get fired on the source cluster, but won't necessarily get fired on the destination cluster. There are some cases that's fine. There's other cases where that's not necessarily a good idea. So let's look at some of the drawbacks of asynchronous replication. There's always going to be a drawback. And it doesn't matter whether we're talking about synchronous replication or asynchronous replication. There's always costs associated with moving data around. So let's look at one of the problems that exists with this today. I mentioned that we move data tablet by tablet, and each tablet does their replication asynchronously, independent of the other tablets. Well, what happens if I use a transaction? A transaction might update multiple records. So you can see I've got a very simple transaction which says update A and update B, and then we commit the transaction. Well, on my source cluster, because Yugabyte recognizes transactions, it's very strongly transactional. I know that my cluster will either see both A and B, so it sees both those changes that I made, or it won't see either of them. There's no other possibilities because they're wrapped in the same transaction. But then I replicate them across to the destination cluster. It's entirely possible that A has been replicated at some point in time, but there's some very short period of time where B hasn't been replicated, or vice versa. B could get replicated before A gets replicated. So at the current implementation, the destination can either see A and B, like it should, neither A nor B, like it should, because they're both valid scenarios, but it can also see A and not B, or B and not A. So the destination at the moment does not preserve those transactional semantics. The other thing it doesn't do is have any concept of global ordering. Imagine I've got A and B again, but in this case, they're not inside a transaction. But A has been applied first, and then B gets applied. Well, on my source cluster, again, I can either see A and B, both those changes, or I can see neither A nor B. But at some point in time, I should be able to see A, but I shouldn't be able to see B. That works really well on the source cluster. The destination cluster, however, has again the same possibilities. It can see A and B, not A and not B, but it's entirely possible that A has been written to the source cluster but hasn't been replicated across, but B then gets written to the source cluster and gets transmitted across first. The vagaries of networks allow you to have that sort of chaos in there. So that means it's possible on that destination to see the record B before you see record A. So it's a concept we call global ordering. So let's look at what's coming down the pipeline to enhance that. In the next major release we're doing, 2.17, we have solved both those problems. So it guarantees transactional atomicity and solves global ordering. And effectively, the way we do it is we're still replicating the data shard by shard. They're independent of each other. But let's say we have three updates that happen, T1, T2, T3. They happen in order on cluster one. And as you can see, they've occurred on different nodes. Therefore, they're on different shards. It's entirely possible, again, by the vagaries of networks, that T1 and T3 have reached my destination. When I go and read that data, however, we know that T1 has happened and T2 hasn't happened, T3 has happened. But we're going to go and read it on the lowest common denominator. So in this case, we're going to read at T1, the earliest time. Now, that means that we're still going to be transactional. We might have T3, but we can't read T3 at this point because T2 hasn't been replicated across. So this gives you that transactional atomicity that you need, and also solves that global ordering. So long as you're reading at the right point in time, it doesn't matter the database actually has other copies of the data. You're only reading the data that should be visible to you. And Yugabyte will sync the tablets to know where it should be and what that time of the reading should be. And that will solve these problems that we just discussed. There's some other improvements coming too. If we look at the current implementation, it's difficult to fail over. It's not terribly difficult, but when we do that, if I'm doing a planned failover, my RPO should be 0. And we want to make this as easy as possible. So we want to make sure that if I'm failing over from my source destination, sorry, my source cluster to my destination cluster, I want to make sure that all the changes from my source cluster have been applied to my destination cluster before I fail over. So my recovery point objective or my RPO should be 0. And there's some improvements coming in the next release, which will help make that a lot easier. With an unplanned failover, because we don't know what has been replicated from our source cluster, the source cluster has now failed, we want to make sure that we have a point in time that we know the good data occurred at and we know has been replicated across. And there might be some data that we don't know the state of for that time. So we can go back to that time where we know the state of the data, but it might be a few seconds before that failover occurs. So the RPO will be low, but it won't necessarily be 0. There's some other things, some technical details. So we're looking at trying to help migrate some of the DDL. You've got two independent clusters. They can have different DDL. Now, if you're trying to replicate the data between them, some of that DDL has to be common. And so one of the focuses is making sure that if there's a mismatch in what the tables look like on source and destination cluster, that you're alerted to this, and replication will be paused until that has been resolved. We're also looking at doing replication at the database level. At the moment, our replication is set up on the tablet level, on the table level, and we want to make sure that if you add tables or indexes to a database, you don't now need to go and say, hey, I want to go and add that data into the replication and make sure it gets replicated. It will be automatic. So that's a very high-level view of what xCluster can give you. I'm going to give you a brief demo, and then we'll wrap up. All right, so what I'd like to do now is go and do a demo of xCluster. So I've got set up here where I have two different universes, one on the west coast of the United States, one on the east coast. These universes are not connected in any way at the moment. They're two discrete universes. I've actually got two terminals, west coast, east coast, and I've set up the same table. I've got one table on them called demo, and you can see that at the moment, there's no data in either of them. If I go and insert a record, so I'm going to insert into value demo Tim, and age of 312. What we can see then is I've inserted on the west coast, there's a value in the west coast, but if I query the east coast, it's not going to be there on the east coast. There's no replication or anything happening between these databases at the moment. So let me just go and delete that record. And we're now back into a clean state with no rows in either database. What I'm going to do now is set up that replication. I'm going to set it up bidirectionally. So we're going to be able to replicate from east to west and from west to east. So I'm going to go into my east cluster. I'm going to come to the replication tab, and I'm going to configure replication. So I'm going to call this west to east and give it a destination of the east cluster. The UI then prompts me for what tables do I want. I can select all the tables. In my case, simple database, I only have the one table, and I'll configure the replication. So now I've got replication set up east to west, but I also want to do, west to east. I also want to do east to west. So I'm going to come into the east cluster, do the same sort of thing. Go into the replication, configure the replication, and this is going to be my east to west. And I'm going to select my target is my west coast cluster. And again, I'm going to select my demo table. Okay. Now, once I see that, I can see that there's a visual indication of the replication. I've got my two bidirectional replications, east to west and west to east. I can see how much lag there is between the data. If I was pushing in a good amount of data, you'd see that number would come up to what is happening in real time. Typically, east coast to west coast, somewhere between 70 to 100 milliseconds. I'm only going to do this for a small amount of data in a demo, so we won't actually see that change, but I'll drill into some of the statistics in a moment. So if I now go back to my consoles, these two now should be linked. I've just gone and configured replication. So let me go and do that insert again. So I'm going to insert the same record, do a select to make sure it's on my west coast. Then I'm going to come to my east coast, and lo and behold, I've got the same record occurred on the east coast. So let's check to make sure that it really is bidirectional. So I'm going to insert a different record. So I'm going to insert record 2, use Sandeep. I don't actually know how old Sandeep is, so we won't tell him. And if we look at that now, select from demo, we can see he's there. And in theory, it should be over this side as well. So we've got both records, and they're replicating bidirectionally between the East Coast and the West Coast cluster. Really easy to set up and configure. And obviously, it's not just inserts. I can do something like an update statement. So I'm going to update demo, set age equals 313, where ID equals 1. And that should reflect there and also reflect here. And of course, we should be able to delete the data too, and that should replicate across. So the whole point of xCluster is that we're really trying to keep the two source and destination clusters in total sync. So all your DML operations will be reflected across. So you can see I've got all my data there. Coming back to the UI, I can drill into these replications. So this is a very simple screen. As I said, because it's such a small amount of data, my replication lag hasn't actually changed, but I can drill in and have a look at the information. I can drill in and see a little graph of what my replication lag was. I can see what my target universe is, and the provider where it is, the tables that I'm replicating, and some metrics. So if this was a real production scenario, you'd be able to see your replication lag as a metrics or a set of some metrics here, there, and the list of tables that you're actually replicating. You can then go and add tables, remove tables, and configure the replication very easily to change which tables you're using. So I hope that was useful, and I'll go back and we'll head back to asking for any questions. So just bring that on slideshow. All right.